Welcome to our 15th video in our series on abstract algebra. In the previous video, we looked at something called the first isomorphism theorem, and we also looked at a lot of really nice examples. And now we're going to look at some applications of the first isomorphism theorem to more general setups. And this will produce the second, third, and fourth isomorphism theorem. And I'd like to also point out that we're not introducing any really new material here. We're just proving results based on existing ideas. Okay, so let's start off by looking at the second isomorphism theorem. So throughout today, G will be a group. And now let's suppose that H is a subgroup of G and N is a normal subgroup of G. Then H intersect N is a normal subgroup of H. And furthermore, the quotient group H mod H intersect N is isomorphic to Hn mod N. So previously we showed that Hn was in fact a subgroup of G. So maybe review how we did that, or when product type groups like this are subgroups. That would be maybe something good to keep in mind. Now, furthermore, I'd like to point out that if H intersect N is equal to just the identity, so the intersection is trivial, then this looks like clearing the denominator. And so notice that H is the same thing as the quotient group H mod the trivial subgroup. But by this isomorphism theorem, that is isomorphic to Hn mod N. And that actually gives some inspiration for our quotient-looking notation for quotient groups. Because notice it looks like we just cleared the denominator here and ended up with H. But of course, that's just carefully chosen notation. Okay, so let's jump into the proof. So we'll start by proving that H intersect N is a normal subgroup of H. So let's suppose that we have H inside of H, and we have N inside of H intersect N. And let's notice that in order to show that H intersect N is a normal subgroup, what we need to do, so we want to show that Hn, H inverse, is in fact inside of H intersect N. So that's the normality condition. Okay, so let's see how we can do that. So since N is normal in the whole group, and all of these H's are in the whole group because H is a subgroup of G, we actually know that Hn, H inverse is an element of N. Okay, but also since everything, so H and N are both inside of H, because N is inside of H intersect N, that tells us that Hn, H inverse is simply a combination of things inside of H. So that means it's inside of H, because H itself is a subgroup. But now putting these two things together, we get exactly what we need. We get Hn, H inverse is indeed inside of H intersect N, from which it follows that H intersect N is a normal subgroup of H, as desired. So now that we've got that, let's define our map. And our map will start over here and end over here, but we'll use the first isomorphism theorem. So let's define the following. So we've got phi, and it goes from H into this quotient group Hn mod N. And looking back on this, I realized that we're actually going to come up with another proof that H intersect N is normal, kind of embedded in this. But that being said, I think it's good to do this on its own, as like it gives you some sort of idea for how these kind of proofs go. Okay, so how are we going to define this map? Well, let's take the element H and send it to the coset connected to Hn. Now, I think this is pretty clearly a homomorphism, but let's just check to be sure. So notice phi of xy will be equal to the coset xyn, but by the multiplication rule in a quotient group, that'll be equal to xn, yn, but that will indeed be equal to phi of x, phi of y. So we're good to go there. I guess maybe to be really careful, we need to say that x and y are in H here. Okay, so this is a homomorphism. Now let's check that it's surjective. So it not only needs to be a homomorphism, but we need surjectivity in this case, and then we also need to calculate the kernel. Okay, so let's take an element of this right-hand side. So let's take an element of this right-hand side, but notice that elements of this right-hand side have a canonical shape. And that is, they are of the form HN, where those are both lowercase, and then capital N. So it's the coset connected to the elements little h and little n. Again, elements of capital H, capital N are of this form right here, which is why elements of this quotient group are of this form. So let's point out that this is most definitely inside of the quotient group that we're working with. And let's maybe be super clear here. So this is for little h in capital H and little n in capital N. But now let's do a little bit of a side calculation. So let's notice that the coset HNN is equal to the coset HN because we have H inverse times Hn is equal to just plain old n, which is in n. And by our coset equality theorem that we use over and over and over again, that implies that these two cosets are equal. So let's make sure we see that that is a lowercase n and not an h. Okay, so that means what we can do is simply map phi of h, or simply map h via phi onto hn. But then by this observation that we made just above, that is connected to the coset that we need it to be connected to. Okay, so we've got it surjective. We took an arbitrary element of the codomain and we landed on that arbitrary element. And now let's calculate the kernel. And hopefully the kernel is h intersect n, and then we can apply this first isomorphism theorem. So let's maybe suppose that we've got an h inside of the kernel of phi. But notice that's equivalent to saying that phi of h is equal to the identity inside of the target group. But the target group has an identity, which is just the identity coset en. Okay, but then let's apply our mapping rule. Phi of h is equal to hn. So here we have hn is equal to, well, the coset connected to the identity, which is simply the subgroup. So we have the coset hn is equal to the subgroup, but that's equivalent to saying that h is inside of n. Okay, but let's also notice that the kernel is a normal subgroup of H. So we have H is in H and H is in N. But that means that we have H is in H intersect N. So putting this all together, we see that the kernel of phi is in fact H intersect N. And now I'd like to point out that the kernel is always normal, so this is another proof that H intersect N is in fact a normal subgroup. That being said, let's apply the first isomorphism theorem. So let's maybe fit that in right here. So the first isomorphism theorem will say that H mod the kernel of phi is isomorphic to the image of phi. But we just determined that the kernel of phi, which was H intersect N, and because we have surjectivity, the image of phi is everything. So making those replacements, we have this result exactly. Okay, so now that we've got this second isomorphism theorem, let's look at a nice application of it. Now let's look at a nice application of this isomorphism theorem. So let's take two natural numbers, m and n, and then let's set d equal to their GCD. and we'll set L equal to their LCM. Great. And now I'd like to make the following calculation. And now we'll start with the following sort of observation, which is well known. And that is that if you take mz plus nz, so that's the sum of two subgroups inside of z, you get dz. So that's pretty easy to check because all integer linear combinations of m and n are multiples of the GCD of m and n, or in other words, d using our notation. Okay, and then furthermore, if you take the intersection mz with nz, you get the LCM z, so you get LZ. And that's also pretty easy to check. Notice everything in mz is a multiple of m, everything in nz is a multiple of n, so everything in both is a multiple of both. But to be a multiple of both, you must be a multiple of the LCM. Okay, now let's get to it. So let's notice that if we take dz mod nz, so first of all, notice that nz is most definitely a subgroup of dz, so this makes sense. So this is going to be equal to mz plus nz mod nz. Just making this replacement of dz with mz plus nz. Okay, so this is cool. Now let's apply the second isomorphism theorem, but our notation here is additive because we have additive groups instead of multiplicative, which we use for arbitrary groups. So that means hn would be replaced with h plus n. That's the additive notation. So if we replace this with h plus n, we notice we have exactly this setup right here. So this is going to be isomorphic to, let's see, mz over the intersection of these two. So again, that's just applying this exactly, keeping in mind that we have additive notation instead of multiplicative notation. But then this is mz mod lz, like that. But then let's also maybe notice that this thing is the same thing as z mod n over d. So that's pretty easy to check with the first isomorphism theorem. And then this thing over here itself is isomorphic to z mod L over m. Again, like pretty easy to check with the first isomorphism theorem. So let's maybe bridge the gap here and notice that following all of these things, we have z mod n over d is in fact isomorphic to z mod L over m. But the only way for two z groups like this to be isomorphic is for their subscripts, in essence, to be equal. So that tells us that n over d equals L over m, but then multiplying and rewriting, we see that m times n is equal to the GCD of m and n times the LCM of m and n. Again, because d was GCD and L was LCM. So this is like a nice arithmetic property, maybe proven in the fanciest way possible. Okay, so now let's look at the third isomorphism theorem. So here we want to start with two normal subgroups m and n of our group G, and then we'll have n is a subgroup of m. Now, you can pretty easily check that this makes n a normal subgroup of m, but we don't have to make that assumption. That follows from all of the definitions. Then the result that we will prove is that G mod n mod the subgroup m mod n is isomorphic to G mod m. So there's a lot going on here. Here we're quotienting a quotient group with one of its subgroups, which is itself also a quotient group, and then we're arriving at a quotient group on the right. And I'd like to point out that this looks like fraction simplification again. Notice if we just think about these as numbers, if you will, and we've got g over n over m over n, then by multiplying by the reciprocal, that would simplify to g over m. Again, this is clearly not what's going on, but it does provide some motivation for our naming convention of quotient group, as well as maybe our notation here. Okay, so now let's get started with the proof, and this proof will also be hinged on an application of the first isomorphism theorem. Let's start with the following map. So it will go from G mod n to G mod m, and it will take the coset Gn to the coset Gm. But maybe think about what we always need to check whenever our domain is a quotient group, or more generally, whenever our domain includes equivalence classes. And that is, we have to check that this function is indeed well defined. And that's because elements of the domain may have different names. And we want to show that they get sent to the same place regardless of which name we choose. Okay, so let's check that it's well defined. So let's suppose that we have xn is equal to yn inside of G mod n. But what does it mean for cosets to be the same? Well, it means that xy inverse is inside of the subgroup n. So like I said, that's what it means for cosets to be the same. Oh, but look over here, we essentially have it. Notice that n is a subgroup of m, so if xy inverse is inside of n, then it must also be inside of m. So just read this from the left to the right, xy inverse is inside of m. But that's exactly the condition for the coset xm to be equal to the coset ym. But now we can just make our replacement with our map. This is equal to phi of xn, whereas this is equal to phi of yn. So we've shown that it's well defined. We've shown that we can take an element from this quotient group that might have different names. By different names, technically here I mean we could take different coset representatives, and we show that they get mapped to the same place. Okay, now let's check that it's a homomorphism, but checking that it's a homomorphism is pretty straightforward, mostly because all of these results are built out of fairly simple maps. Okay, so let's check, like I said, that it is a homomorphism. And we'll do that by looking at phi of, let's see, xn times yn. So that's a product occurring in the left-hand side. But this simplifies to phi of xyn using the operation inside that quotient group G mod n. But now this is going to be xym using the definition of the operation, or sorry, using the definition of the mapping. But now reversing this, we get xm times ym, but that's exactly phi of xn times phi of yn as needed. So we've got a homomorphism. Now let's check that it is surjective. So this is another thing that's kind of made to be surjective. So let's suppose that we have gm inside of G mod m, and then note that phi of gn gets mapped to gm. So there, we found a pre-image for our arbitrary element. Okay, and then what do we do from there? Now we want to calculate the kernel. So what is the kernel in this case? Well, looking over here at our result, we hope the kernel is this group M mod n, but we'll get there. So let's suppose that Gn is inside of the kernel of phi. But let's notice that's equivalent to saying that phi of Gn is equal to the identity element in G mod m, but that's the coset attached to the identity em. But next up, we can use the function rule for phi, and that'll give us this equation, Gm is equal to m. Just keeping in mind that the subgroup is equal to the identity coset. But now we've done this 100 times so far. If you have a coset equal to the subgroup, that means the representative must be inside of the subgroup. So that means we have G is an element of M. So let's see what we've got. We've got Gn is in the kernel if and only if G is in M, but notice that that means that the coset Gn is in fact in the subgroup M mod n, because this representative here must be inside of M. But now putting all of this together, that tells us that the kernel of phi is equal to M mod n. Okay, and then really there's only one last thing to do, and that's apply the first isomorphism theorem to finish this thing off. So let's notice that the first isomorphism theorem will tell us that G mod n mod the kernel of phi is isomorphic to the image of phi. But then pushing that in both directions, notice that the image of phi is everything because we have a surjection, and the kernel of phi is that quotient group over there, M mod n. So we have G mod n mod M mod n. And then following this from the left to the right, we have the desired result. Okay, now let's look at a nice application of this. Now we've got a nice corollary of this third isomorphism theorem. It says that Zn mod the cyclic subgroup generated by M is isomorphic to Z GCD of M and N. Okay, so let's see how we can do that. So let's maybe set D equal to the GCD of M and N just for simplicity. And now let's recall that we previously showed, so previously on this series on abstract algebra, that the cyclic subgroup generated by M was the same thing as the cyclic subgroup generated by D. So this is maybe like a preferred generator, this one that is albeit a bit smaller. And let's also notice that we know the size of this group. Again, that's by something we did previously. This is in fact a cyclic group, really a cyclic subgroup of order n over d. So since this is a cyclic subgroup of order n over d, we know that this must indeed be isomorphic to Z mod or Zn over d. Because all cyclic groups of the same order are isomorphic, and this is also a cyclic group of order n over d. But now reusing the observation we used in our previous application, this is isomorphic to dz mod nz, where this top group is all multiples of d, whereas this bottom group is all multiples of n. And now we're essentially ready to finish it off. So let's do that. So we'll have Zn mod, the cyclic subgroup generated by M, will be isomorphic to Z mod Nz mod. This Z mod Nz is the copy of Zn. And then the cyclic subgroup generated by M will replace with dz mod nz. Great. But now we can apply this isomorphism theorem to simplify the fraction, if you will. And if we simplify this fraction, we get Z mod dz, which is in fact isomorphic to ZD as necessary. And that's really all there is to it. So now that we have this, let's do some quick examples of this in action. So this is essentially just going to be applying this to special numbers. So notice if we take Z24 and mod it by the cyclic subgroup generated by 15, we should get something isomorphic to Z and then the GCD of 24 with 15, which is Z3. Okay, and then if we go Z36 and mod it out by the cyclic subgroup generated by 24, we in fact should get Z12. And that's because 12 is the GCD of 36 and 24. And then you could do tons of other examples like this. And in fact, you could also do some multiplicative cyclic group examples very, very similarly. So notice if we took like C18, and let's say that is the cyclic group generated by G, and we did C18 mod the cyclic group generated by G to the maybe 10, we should get something which is isomorphic to C and then the GCD of 18 with 10. But what's the GCD of 18 with 10? Well, that is 2, so we should get C2. Okay, so if you want to use additive notation, you have something like this. If you want to use multiplicative notation, then it's essentially the same thing. You just push things up into exponents. Okay, now let's move on to this fourth isomorphism theorem. Now for the fourth, or sometimes called the lattice isomorphism theorem. We'll see why it's called the lattice isomorphism theorem. So it says that if we've got a normal subgroup G, then every subgroup of the quotient group G mod n is of the form H mod n, where H lives between n and G. So in other words, you can't really have a subgroup of a quotient group without having some sort of group in the middle of that quotient group in the whole group. Okay, then furthermore, there's a bijection between the following two sets. So the first set is the set of all subgroups of G that satisfy the condition that n is contained in that subgroup. And the second set is the set of all subgroups of G mod n. Okay, so let's maybe prove this first bit first, and then we'll construct the bijection. Okay, so let's start with some sort of subgroup of G mod n. Okay, so we've got K, which is a subgroup of G mod n. And then next, let's take K to have the following shape. So we'll say that K is equal to, well, it's going to be equal to a bunch of cosets, Gn. We know that it's going to be made up of cosets because it itself is a subgroup of G mod n. And then any coset that's inside of K will put that representative into a new set. And that new set we'll call H. So maybe this is like a little bit confusing and seems a little bit circular, but let's maybe outline what's happening here. So we'll build H by the following rule. So G is inside of H if and only if Gn is inside of K. Recall that K again is a subgroup of the quotient group, so it contains cosets. Okay, so at this moment, H is only a subset. And I said at this moment because really that's for now. The thing that we will immediately prove is that it's in fact a subgroup. Okay, so let's actually make that into a little intra-proof claim. So I'll write that here. So our claim is that yes, in fact, H is a subgroup. So that means I can use this pointy notation instead of the round notation of a subset. So let's first show that it's non-empty. So it's pretty straightforward to show that it's non-empty because we get the element E is in H because we know that the coset attached to E, En, must be an element of K because K itself is a subgroup of G mod n, and any subgroup contains the identity. So what this tells us, like I said, is that H is non-empty. So that means we can get off the ground talking about H in the first place. I guess that's probably pretty clear because we know that K is non-empty, but if K is non-empty, then H is most definitely non-empty. So perhaps this was overkill, but I kind of think that's okay. Okay, so now let's use the subgroup test. So let's suppose that X and Y are both in H, and what we want to do is show that X, Y inverse is in H. We use the subgroup test all of the time. Okay, but the condition for X and Y to be in H is the same thing as the condition for Xn and Yn to be in K. But now we're going to use the fact that K is a subgroup of that quotient group. So that tells us that xn and then yn inverse is inside of K. Again, because we know we have a subgroup of that quotient group. But then by the group rule in the quotient group, that means that the coset xy inverse is inside of K. But if this coset is in K, then that tells us immediately that xy inverse is inside of H, by the way that we're defining H. But starting here and ending here means that H is indeed a subgroup of G. So we've shown that H is a subgroup of G, and in fact, we've shown that all subgroups of G mod n are of the form H mod n, where H lives between n and G. And now let's just build our bijection here. Okay, so we need some tools to build this bijection. So let's consider the following projection. So this is like maybe the standard projection map from G to G mod n. I'll call it pi. So we've got pi goes from G, like I said, to G mod n. And of course, by the standard projection map, I mean the one that takes G to the coset Gn. Okay, and then you can also maybe check on your own that this is what it does to a subgroup H. It takes the subgroup H into the quotient group H mod n. And then you can check pretty easily that pi of H is equal to H mod n, where of course this is the image of the subgroup H of G under our map pi. But what we really want is not something like this. A map like this operates on elements. We want a map that operates on subgroups. You might say, well, it's operating on subgroups here, but not really. This is like the image of the subgroup under the map. So what we'll do is define a map F, which is notated over here, so it's from here to here, by the following rule. So F evaluated at the subgroup H equals pi of H, which equals H over n. Where now this isn't really the image of the subgroup because the domain of F is actually subgroups. Okay, so anyway, let's check that this is injective, and then after that we can check that it's surjective. And this is not a homomorphism, so this is just a set theoretic map. So let's suppose that f of h1 equals f of h2. And let's observe that that means that h1n equals h2n. And then what we want to show is that h1 is equal to h2. And we can do that by double set inclusion. So let's suppose that little h is inside of h1, but let's notice that that means that the coset hn is inside of h1 mod n, which is equal to h2 mod n, but by the structure of elements inside of h2 mod n, that tells us that h is in h2. So putting this together, we see that h1 is a subset of h2. And then you can do a symmetric argument to show that h2 is a subset of h1, and then this finishes this thing off. So I'll just let you finish off the details. It's pretty much the same. So next up, let's show that this is indeed surjective as well. And we'll use the first part of this theorem to show that it's surjective. So let's suppose that K is a subgroup of G mod n. Remember, elements over here are just subgroups of that quotient group, but that means that K indeed equals H mod n with H living between N and G. And then finally, we can just make the observation that F evaluated at H is H mod N, which is equal to K. So we found something that gets mapped onto that K. So we've got something that's injective and surjective, which means it's bijective, which means these two sets have the same size. In other words, and this is how you often see it written, there is a bijection or a one-to-one correspondence between subgroups of G mod n and subgroups of G that contain N. So that's the standard way of writing this. And now let's look at an example of why this is called the lattice isomorphism theorem. Okay, so for example, let's consider the map phi from D4 to Z2 cross Z2. Let's recall everything in D4 can be written of the form S to the A, R to the B, where A is just 0 or 1, depending on if it's a rotation or a reflection, and B is either 0, 1, 2, or 3. Because we've got 90-degree rotations here, these are the symmetries of a square. And then we'll take this to AB, like I said. And let's notice over here, this is a full description of this mapping. And with elements of small groups, or with small groups, it's nice to look at a full picture like this. So the identity gets mapped to 0, 0. R squared also gets mapped to 0, 0. That means that the identity and R squared are both in the kernel. And let's notice that those are the only things that get mapped to 0, 0. Notice that R and R cubed get mapped to 0, 1. And then S and SR squared get mapped to 1, 0, whereas SR and SR cubed get mapped to 1, 1. Okay, but this thing is also onto. So that means we can apply the first isomorphism theorem to get the following result. So D4 mod the kernel. I've got the kernel there in those yellow boxes, but notice that's just the cyclic subgroup generated by R squared. So this is isomorphic to the image, which is Z2 cross Z2. Okay, so now let's make a subgroup lattice of this thing right here. Well, D4, and then we'll apply this rule over here to D4 and the cyclic subgroup generated by R squared, where that is taken to be our N. Okay, so let's put D4 up top, and then notice that it has 8 elements. We've got 3 subgroups with 4 elements. We have this cyclic subgroup generated by 4, so that's a subgroup with 4 elements. We have a subgroup generated by S and R squared. That's like a copy of D2. And then we've got another copy of D2 over here, which is generated by SR and R squared. And then underneath this R is the cyclic subgroup generated by R squared. And then branching off from here, we have the subgroup generated by just SR, as well as the subgroup generated by SR cubed. Great, so notice this line here is all of the subgroups of order 2. Then branching off this, we have the subgroup generated by SR squared, as well as the subgroup generated by S. And then finally at the bottom here, we have the identity subgroup, so it only has the identity. So there's our full subgroup lattice here. And now I'd like to notice that R squared is playing an important role. This is playing the role of N over here. And then I left out 2 lines here. I've got lines that go here and here. And notice, what subgroups do we have of D4 that contain R squared? We have these 1, 2, 3 in the middle. So we could maybe put double lines here for these subgroups of D4 that contain R squared. And now let's compare that to the subgroup lattice of Z2 cross Z2, which is a group of order 4. So we have 3 cyclic subgroups of order 2. We have the one generated by 1, 0, the one generated by 0, 1, and finally the one generated by 1, 1. Those are all of order 2, and then we've got the identity subgroup down here, which the identity in this case is 0, 0. And let's notice that this lattice right here is exactly the same as our yellow lattice here. So in other words, if you've got a lattice for an entire group, you can get a lattice for the quotient group pretty easily. You just go down to the normal subgroup that you're quotienting by, and then look at all paths from that normal subgroup up to the top. And that will build you the subgroup lattice for the quotient group itself, which in this case we used an isomorphism class. Okay, so now I'm gonna give you some extra. Here I've got 3 nice warm-ups. And the first two seem quite general, but they kind of follow the same idea from the second and third isomorphism theorem. And that is to carefully build your setup and then apply the result of the first isomorphism theorem. Okay, so for the first one, let's take normal subgroups of G, M, and N. And these are specially chosen so that G is equal to Mn. Then G mod M intersect N is isomorphic to G mod M cross G mod N. So this is some sort of generalization of the result that we had previously about internal direct products. Next, let's suppose that N1 is a normal subgroup of G1 and N2 is a normal subgroup of G2. Then show that N1 cross N2 is a normal subgroup of G1 cross G2, and that the quotient group G1 cross G2 mod N1 cross N2 is isomorphic to G1 mod N1 cross G2 mod N2. And then finally, let's make a diagram exhibiting the lattice isomorphism theorem for Q8 mod the cyclic subgroup generated by -1. And that's a good place to stop.